Hey, welcome back. Today we're going to be talking about an AP Physics C Mechanics FRQ number 1 from 2022. This is from set 1. I'm going to talk you through it. This FRQ has some really crucial ideas that are useful for almost any AP Physics C Mechanics student, and so let's go ahead and get to it. Okay, so let's start by reading the problem. This is actually surprisingly hard, I think, for a lot of students to pay close attention as they read. It is good to get a quick glance at the diagram of what's going on to help us to understand it. So number 1 down below says a block of mass M is pulled across a rough horizontal surface. So notice that this implies that there is friction here. Horizontal table by a string connected to a motor that is attached to the floor. The string passes over a pulley with a negligible friction. Okay, so we're going to ignore the pulley in this process. And that means the tension here, the tension in the line, is going to be the same tension on the motor that you would have on the block. Okay, the next sentence says the pulley is at height h above the table. The motor exerts a constant force of tension. And they're defining tension as F sub t. I've written F sub t many times, but I've also written just tension. I typically just write like T for capital tension. Here, I personally am going to have to be careful to write this as F sub t. So why do I talk about that? Because I think you should be thinking the same things as you read through this problem. So I'm going to do my best to model exactly how to tackle this problem as you go through it. So it says force of tension Ft on the string, and the block remains in contact with the table at all times as the block slides across the table from x equals L. So this is our initial position right here, to x equals 0, and that's a little bit off, and I'm going to point that out now, and I'll come back to this at the end of this lesson because our final position here is going to be x equals 0. That may throw you off a little bit, so just be careful with that. It then says the coefficient of kinetic friction between the table and the block is mu sub k. Express all algebraic answers in terms of m, fair enough, h, f sub t, really important, I need to focus on that, so I might circle that. X, fair enough, mu k, and L. So we can use tension. It's really crucial to understand that they're saying that tension in this problem can be treated as a fundamental force. It doesn't need any further derivation. You can just treat it as is. So that's really important here. And then we also have physical constants as appropriate. What is that talking about? In this case, we're talking about g. We can use g, gravitational acceleration, in our solution. Alright, so let's take a look at the first part of the problem. A, it says on the dot below that represents the block, draw and label the forces, not components, that act on the block when the block is at x equals L. Alright, so it's at this initial position right here. Each force must be represented by a distinct arrow starting on and pointing away from the dot. So really important, we're going to draw our first tension arrow, and what they're saying is don't draw it like this. This you actually will lose easy points for. There's no reason why you should lose points on a free body diagram. Also, really important, my tendency would be to write this as a capital T. In this case, we're going to write this as an F sub T. Be careful with that. What else do we have? Well, of course, we've got gravity. We've always got gravity right here. So we could call this Fg. We can also call it Mg. Either way you want to write that is fine. We always are going to have a normal force in this case because it's in contact with the surface. Have to have a surface for a normal force. And then we have an Fk. In this case, I'm going to call it Fk because they've already given me a mu k. I'm going to work with that and just say, all right, that's kinetic friction. Even though on our equation sheet, it's defined as F sub F for general friction. They do that, by the way, to write one equation as opposed to two on your equation sheet. Okay, so that will give you full points here for A. Let's take a look at the next section. Okay, and so the next problem says, derive an expression for the angle theta that the string makes with the horizontal as a function of x. So this is really important. They're not saying in terms of the force or the acceleration. They're saying in terms of the position. This is a little bit different and really important to think about, because if you're a little unsure where to go with this, it's really confusing, but it's actually easier than you might think in a way. Let's think about this. We know that we have this theta here. We're going to call this x, and what else do we know? Well, we know we have an h value here. We don't know what this is. We do know that we have an angle theta here. How could we solve for that unknown hypotenuse? What do you think? Well, we could use the Pythagorean theorem, of course, right? So this is just going to end up being h squared plus x squared all under a root. That'll be our hypotenuse here. In fact, if you write that in at this point, that would be fine, although if you need to show the work for that, go for it. This is a right triangle right here. All right, so what I really want to emphasize though is I want you to not do this. Here's the problem. So if you were to write this out and you were to say, well, I know I've got like force tension over here and I've got an X value right here, maybe I could do that. And the answer is no, you cannot do that. That is sad face. That will end up in disaster. In other words, this is in newtons, this is in meters over here. You cannot mix and match your variables and especially your units the variables are measured in terms of a right triangle. It just simply will not work. So please avoid that issue. Just don't do it. What you can do though, notice that these are all in meters over here. They're all essentially in the same type of unit or type of measurement that we're working with. All right, so let's go ahead and write a expression for this. I can think of 3 off the top of my head. I'm going to say the sine of theta is going to be equal to h over the square root of h squared plus x squared, as that's going to be our hypotenuse right there, so opposite over hypotenuse, and that could work. You could also write a version of this for cosine or tangent. And then don't forget at the end of this, we do need to take the inverse sine of both sides and solve for the angle that's involved, because that's what we're being asked to do. Okay, and next up for C, it says derive an expression for the normal force Fn exerted on the block by the table as a function of the block's position x. So notice that they are labeling this normal force as F sub n. We should try to match their variables as well. Even if you typically write this as a capital N, write it as an F sub n here. And at this point, we're dealing with multiple forces. It's really, really comfortable for my students, and if you've been tracking with me throughout the year, to be able to think about the sum of the forces in the x-axis, sum of the forces in the y-axis. They do define to the right as positive and up as positive, so we're going to stick with that convention for now. So what forces do we have in the x-axis? Well, we've just got 2. We've got the force due to kinetic friction, and we've got the force of tension in the x. That's all we have. The sum of the forces in the x is equal to mass times acceleration in the x. In this case, we actually don't know if it's 0 or not. It's unclear from the problem. In other words, if we were to go back and reread that, they do not make it clear in the problem. So in that case, we're just going to assume that there is some acceleration. It's safer to assume that than to assume that there is 0 acceleration. So we're going to say Fk minus Ftx is equal to mass times acceleration in the x. So the next portion, let's go ahead and work in the y-axis and think about what's happening here. Sum of the forces in the y, we have Fty, and we have an Fn, and we have a negative Fg. Fg we're going to sub in little mg, and the second line of the sum of the forces strategy is just mass times acceleration. At this point we need to ask ourselves, is our acceleration on the y something or nothing? Well, the answer is nothing. It's not moving at all in the y, so it's going to have a 0 acceleration. That means we can set these equal to each other and say Fty plus Fn minus mg is equal to 0. Notice we're being asked for Fn, so that's good. We can isolate for that. We can say, well, Fn is equal to mg minus Fty. All right. You may have noticed a problem here. Function of the block's position in terms of x, this is a problem in the sense that we have nothing in this equation in the y-axis that's going to help us in the x-axis. Okay, let's take it one step further and see if we can find something helpful. Remember, Fty is going to be Ft, and if we think about what it is, we've got this theta right here. This is Ftx, this is Fty, this is Ft over here, and so our Fty is going to be Ft times the sine of theta. So that's going to be our Fty. Alright, now at this point we could say we're still stuck. We don't have any information about this in the x-axis at all. That's a problem, but we did say something previously about the sine of theta. So how do we go about relating this triangle right here, which is all in forces, with our previous triangle that we had talked about, which looks something like this, where this was x and this was h, and we said this was the root of h squared plus x squared. How do we relate these things? Well, we can still say that the sine of theta is some value in terms of x, right? Well, if we solve for that sine of theta, we can say sine of theta is going to be equal to h over the root of h squared plus x squared. If we take that and sub that in to the sine of theta, then we have our normal force in terms of the function of the block's position. So I need to drag this up to give myself a little bit more room so we can see what we're doing here. We're going to say Fn is equal to mg minus Ft. Remember, we can just leave Ft as is because they told us we could. And then we have to say, well, this is going to be h over the roots of h squared plus x squared. Okay, let's box this because we may need to come back to this later. Okay, and so next up what we have is this equation already. I've already done this, but this is what we're going to put in ftx. Let's go back to that and think about that. So if we said ft, we said was like this. ftx is going to be over here. This is our theta. So in this case, we're going to be using cosine. So we'd say ft times the cosine of theta is going to be ftx, right? And we had set something up previously. We need to redraw this because I'd solve for the sine version of this. We need the cosine version of this. Let me explain what I mean. We've got x and h here because we can't use forces and position on the same right triangle. So as a result, we had said something like this previously. I'm going to go ahead and show you what we mean. This is going to be h squared plus x squared is going to be the resultant here. So the cosine of theta, one aspect of that, is a function of the position x. Really important here. This is why we're doing this. We need to be able to put this in terms of x. That's adjacent, so that's x over the hypotenuse. In this case, that's going to be the root of h squared plus x squared. So that's going to be our cosine of theta. We can go ahead and sub that in here and continue with our work. So we're going to say f net is equal to fk minus ft, and then we're going to put this business in here, x over the root of h squared plus x squared. They do ask for the magnitude, so we could treat it as such. Make that clear by putting in our absolute value signifiers here. Okay, and one more step that we need to take is we can't really leave this as Fk. In other words, they haven't given us Fk as one of the fundamental forces that we can work with. They gave us Ft. They basically said you can stop deriving an Ft, but you can't do that with Fk. So we need to figure out what Fk is going to be. Remember, our force due to kinetic friction is mu k times Fn over here. And so we can take that and sub it in over here and say F net is equal to, and again, Fn is not something that we have been able to just stop with. We need to further define what we mean by Fn. So we can write it like this. I'd said this previously, that we need to keep track of something. I'm going to show you what we had solved for previously so that we can easily sub that in. So that's going to be, and let me just double check my algebra really quickly to make sure I've written everything in perfectly. This is surprisingly difficult to make sure that you've not made a little error that'll throw off the entire problem. I have not. I'm just going to rewrite this h to make it a little more clear. This is h squared underneath this root. In any case, that's how you would do that section of this FRQ. Okay, and so D says, write but do not solve an integral expression that could be used to solve for the work done by the string on the block. The block moves from x equals L to x equals 0. So this is what's on your equation sheet right here. And what we really want is, in this case, we'll call this dx. X is kind of a stand-in for r. They're basically the same thing, just labeled differently. So we're going to use that here. But really, we're interested in this force that's in the x-axis. That's why you have this dot right here. It's a dot product, meaning that you're really interested in the force in the x-axis. I could summarize this without calculus briefly, just to kind of clarify this. We're talking about the force parallel times the distance through which that force is applied. That's what we mean by work. Let's think about this. We could say work is equal to the integral of ftx dx. Don't forget to make the force negative as is shown here. And another way of writing that would be work is equal to the integral of negative ft. And then we want to think about what the x component of that would be. Remember, we had ft like this. So this is going to be ftx. And so you could say ft times the cosine of theta is going to be ftx. Now, really important that we notice we need to do the integral in terms of dx. We need to get that x value in here. And we don't currently have the x value in here at all right now. So this we can sub in for the ftx business right here, dx. In other words, we still have this in newtons with no x value. So how do we do that? This is a recurring theme for this problem, although it's an incredibly useful and important skill. If we go back and think, well, the only thing that we can do that is the same from both of these right triangles is we can talk about that theta is the same. So that relationship here, the cosine theta, is going to be the same thing in both triangles. In other words, we can translate from forces into x values and x values in the forces using that theta. And so that's what we're going to do here. So in this case, we could say cosine of theta is going to be equal to x over the root of x squared plus h squared. So we can say, therefore, the work is equal to the integral of ft x over the root of x squared plus h squared dx. Now, we're not done. We've got limits. This is something that I had mentioned earlier in the problem, and that is this. Our final position is actually 0. And remember, your final limit is going to be up at the top there of 0, and this is going to be L over here. Even though it might be tempting to reverse that because of practice, in this case we're doing the opposite. We're actually stopping at 0, so be careful with the upper and lower bounds as you finish out this section of the problem. Okay, and last but not least, the question says, does the string do more or less or the same amount of work in the block as the block moves from x equals L, so the initial position right here, the first half of this, to L over 2, this is L over 2. So essentially they're asking about, does it do the same amount of work in the first half of this, or less work, or more work in the first half of this? Well, remember, work we're talking about involves force parallel to the motion, and the force parallel to the motion actually gets less and less as time goes on. In other words, if we had the box, like say right here, this angle would be more extreme. It would be closer to 90 degrees the closer it gets to the edge here, and there would be less work being done because there is less of this tension in the x as compared to previous. So we would say there's more work being done when the block moves from x equals L to x equals L over 2, and we can justify it. They do ask you to justify your answer, so you could say in the first half rather than the second half, and then work is done in the same plane as the motion itself. And so that's how you would approach this lesson. I've gone over lessons for an entire year of physics and most of the concepts of AP Physics C mechanics. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.